The opportunities for technology transfer from this mission to go to the moon and Mars and grow plants for human life support. You go to the moon and Mars, you can't throw anything away. We don't know how to do that yet. Learning how to do it in space will definitely improve our chances of managing ecological contexts here on Earth.
The Rational View is a weekly series hosted by me, Dr. Alan Scott, providing a rational, evidence-based perspective addressing important societal issues. Hello and welcome to The Rational View. I'm your host, Dr. Al Scott. On this episode, I'm going to be interviewing a guest to discuss bioregenerative life support systems. And that's basically the use of plants to support life in space. You may remember this from the movie The Martian by Matt Damon, where he grew potatoes from his own poop to survive. Now, this isn't exactly what our guest does, but he's been a leader in Canada, and we go way back. This is something that I've also been involved with, and it's a lot of fun, and I'm looking forward to bringing it to you. Before we get into the interview, I've got a little bit of news for my listeners. I'm starting a Facebook discussion group. I'd like to get some more interaction, get some input from my listeners, maybe some ideas on new podcasts, talk to you. It's going to be called TheRationalView on facebook.com/groups/TheRationalView, all one word. And I'm going to be opening it on Pi Day, March 14th, 2021. So if you request to join this group by Pi Day, I'm going to include you in a draw for my new swag. Some Rational View t-shirts are going to be available. So please join my group. I'm going to give it a t-shirt to one lucky group member. And I'm going to hold a Facebook Live as part of my grand opening. So I'm going to talk to you, everyone who's in the group. I'm going to go live on Pi Day at 3 p.m. Eastern Time, and we'll chat. See if you guys have any questions. It'll be pretty informal, and maybe we'll be able to speak. So thank you for listening, and back to the interview. If you enjoy what you're hearing, please press like. Please share it with your friends. I appreciate you listening, and I hope you enjoy this. Dr. Mike Dixon is a professor in the School of Environmental Sciences and director of the Controlled Environment Systems Research Facility, University of Guelph. He served as the chair of the Department of Environmental Biology from 2003 to 2008. Professor Dixon joined the university as an NSERC University Research Fellow after earning his PhD from Edinburgh University in Scotland and holding a post-doctoral position at the University of Toronto. As project leader for the Canadian research team investigating the contributions to plants to life support in space, Professor Dixon formed the Space and Advanced Life Support Agriculture, or SALSA, program at the University of Guelph. This program currently represents Canada's main contribution to the international space science objectives in biological life support and collaborates with NASA and the Canadian and European space agencies. Professor Dixon's CESRF facility is among the world's leading research venues for technology developments and research dedicated to studying plant and microbial interactions in advanced life support systems. The technical pull of space exploration has aided the development of a wide range of technologies that have spun off into applications in terrestrial agri-food sectors, and most notably the phyto-pharmaceutical sector in recent years. Thanks for coming on the show, and welcome to The Rational View.
Well, thanks, Al, and it's good to see you again.
So, in addition to your extensive professional accolades, I happen to know that you're also famous for your extensive collection of single malt scotch, of which I've had the distinct pleasure to partake on more than one occasion.
That's right. I guess I've probably in the neighborhood of about 300 different single malts in the Scotch bar in the basement, and it's that venue, as you know, has been the place where a lot of Canada's participation in space science has taken place.
Indeed. And quite a good venue it is. Thank you.
Oh, by the way, I'm on February 20th. We'll be launching barley seeds to the International Space Station, and they will live on the MISSI platform. Alpha Space has taken care of that for us. And so we have a project which is sponsored by our good friends in Scotland at the Glenlivet Distillery.
Wow. So they're sending up seeds to the ISS.
That's right. We're putting that. This is kind of one of those little incremental steps that we're taking in biological life support, plants in space, food, life support, etc. We want to see what extremes our seeds, the engines of our life support ultimately, what kind of extremes those seeds can undergo and still come out swinging at the other side. And we've been, as you know, with the Tomatosphere project for the last 20 years, we've been sending tomato seeds into space to the ISS, and they come back, and school kids across Canada do germination trials. And over the last 20 years, we've discovered that anything up to, I guess, 19 months on the International Space Station has no significantly negative effect on the germination potential of tomato seeds. But this will be the first time we put seeds outside the ISS on the MISSI platform, which exposes it to the extreme vacuum and temperature swings of outer space.
Not to mention the radiation.
Exactly. The NASA has also a project. Biological payloads on the MISSI platform are rare. In fact, I think these may be the few. The Tomatosphere project put some tomato seeds on the MISSI platform last year, and they have just returned. And I'll be doing germination tests on them as soon as we figure out how to get them across the border.
Now, that Tomatosphere project has been highly successful. That's a great outreach for space exploration and agriculture.
Oh yeah, it's been fun. I mean, it's been a hoot for the last 20 years. Bob Thirsk and I and Ron Thorpe from who used to be the head of the CEO of the Mark Garneau Collegiate Institute in Toronto. The three of us sort of dreamed this up back in the late 90s, and then in 2000 sent a package of seeds up with Mark Garneau on his last shuttle mission, and so he brought them back after they went around the world with him a few times in the shuttle, and since then we've had a few ISS missions, payloads, and now we routinely go up on SpaceX or on the Dragon, or any number of different options we have now. Blue Origin has taken our seeds up just recently as well, just to low Earth orbit. So it's been, and we've hit over 4 million students across North America in the last 20 years. So as a science education and outreach element of our program at Guelph, it's been remarkable.
Yeah, I've actually been a mentor in the Tomatosphere program for a class that my daughter was in, actually. And so they get these seeds that have been up in the space station, and they plant them, and they measure the growth of the tomatoes against a control set of tomatoes and report the results and learn how to do science. It's really an excellent program. Yeah,
it covers the waterfront in plant science, space science, nutrition science. There's and just the scientific method.
Mm-hmm. Very important.
STEM coverage, science, technology, etc., is handled very nicely with that one simple experiment.
So let's step back a bit, and can you maybe describe for our listeners what is advanced life support agriculture? What does this entail?
Well, food, as you know, is limits how far from Earth we can go and how long we can stay. So it is the main driving variable in human space exploration. If you saw The Martian, you saw Matt Damon sitting there doing his arithmetic on the potatoes and how long that source of nourishment would sustain him. And that arithmetic is exactly what we do. Variations on it and developing the technology and arriving at the research questions that we ponder in trying to see how long and how successfully we can have plants providing all the functions of human life support.
So your program is basically the science behind Matt Damon's The Martian movie.
Well, the science was originally the NASA's BVAD, Basic Values and Assumptions document, which has recently been updated. So they were basing it on some relatively old arithmetic. But fundamentally, the Martian actually had some of the most reliable science of any of the science fiction movies of late. Well, except for the wind. They have that force of wind at an average atmospheric pressure of 0.6 kilopascals. Just to mess my hair, it'd have to be a couple hundred miles an hour. So that was a little bit of a stretch. But hey, we give Hollywood their leeway.
So, Mike, you and I wrote a roadmap for the Canadian Space Agency to develop a greenhouse on the moon. In the early part of this decade, the CSA had just put a robotic arm, or I guess this millennium, the CSA had put a robotic arm on the International Space Station, and they were hosting a series of workshops on what should be the next big thing in Canadian space exploration. And I remember at one of these workshops you made a very convincing case that growing plants in space could be an ambitious cross-disciplinary Canadian niche in space exploration. And I was struck by how important this research seemed because of its potential for dual use. Could you describe why this project is such a great story for Canada?
Well, it was at that time. You're recalling, a brief spike in the interest of the Canadian Space Agency in the life support agenda, biological systems, plants in space, etc. And you're right, we did generate quite a bit of interest. I recall you and I went to Russia at one point at a high point in that. And that was the last high point, as I recall. So Canada comes by its ownership of some leadership in this arena, quite honestly, because we are, a pretty miserable place. I'm looking out the window now at 2 or 3 feet of snow in my front yard, and we grow plants under these conditions. And Canada's north is the next worst thing from the surface of the moon in terms of a harsh environment to try and grow plants. And we're pursuing that agenda with the technology transfer of our program at Guelph to address food security in the north, and indeed food security in other harsh climates on the planet, such as the deserts of the Middle East. So there's a great deal of opportunity for taking the technical pull of going to space and solving the problems of recycling and just production and maintaining a reliable life support machine. There's such an opportunity to transfer that technology to terrestrial agri-food sectors, and that's what our industry partners are all about.
Yeah, I remember we actually went up to Yellowknife as well to try to develop a collaborative project to provide critical infrastructure for remote northern communities that are typically, they get their food shipped in from Mexico. There were a lot of challenges, as I recall, with setting this up, and we had a study with the Aurora Research Institute to show that it seemed like it was commercially feasible to actually grow in situ these high nutritional value plants like strawberries and tomatoes. And I was doing the engineering work, and your group was looking at the horticultural processes. And the biggest technical hurdles for these small communities was the power for heating and lights. Many of these places just run on diesel fuel when it's cold and dark out there. Now, this ties into another interest of mine, which is nuclear power as the solution for all of our ills. And small modular reactors would be a key technology to support food production systems.
And you're right. I mean, if you have to grow your tomatoes in a snowbank in Yellowknife using diesel power, then you may as well continue to air freight them in from Mexico because the cost benefit is questionable. However, as we learned, and in our work, and in that project, we had the Arctic Energy Alliance as one of our partners as well, and they made it clear that you needed to solve the energy problem, the energy supply issue with multiple forms of alternative energy, hydro, and you needed to get the buy-in of the local governments basically to offset extraordinarily high energy bills in that part of the world. So if you have multiple sources of alternative energy like wind and solar, and then hydroelectric power, of which there is some in various areas of the north, but then you need special deals with the power generating institutions to help you establish the horticultural entrepreneurs in that sector. You need about 10 years of sweetheart deals with energy to really get it off the ground and establish the background, the technical support backdrop against which these kinds of industries need to, there isn't a home hardware store down the street that you can rely on. So it's a challenge. And you mentioned that roadmap for putting plants on the moon. I had occasion to revisit that documentation recently, and you and I served on the Advanced Life Support Working Group for the CSA back at that time. And I revisited that because we were in the process of making a proposal for a phase 0 study at the Canadian Space Agency to do exactly that again. This whole the life support and plant biology in space, and the recognition that food drives the equation, and we have the technology and expertise in Canada to address harsh environment food production. So exploiting that community and addressing the technical challenges in space is now back on my near horizon. And in collaboration with Canadensis, I don't know if this is supposed to be a secret or not, but in collaboration with Canadensis, we have the Phase 0 project assigned by the Canadian Space Agency to design the next system, to put a system on a lander on the moon, to start making those incremental steps that must be taken to advance biological life support.
And the science behind this is quite interesting. I think it's, for one of the reasons I got involved with this is because I could see the importance of this from an ecological standpoint. We don't know what the minimum system is to sustain human life. We don't know the ecological carrying capacity of the Earth. We can't yet build an enclosed ecosystem that survives on its own with people in it indefinitely. We don't know how to close that loop yet. The Earth does it. We know that a system the size of the Earth is able to recycle all the nutrients in whatever time scale it takes for all the nitrates and all of the ions that we need to be recycled from our poop basically back into plants and continue supporting life seemingly indefinitely. But we don't know what is the carrying capacity. And this has a lot of, I think, feedback in terms of population density and sustainability. So the science that you're looking at is not only key for surviving in space, it's also key for surviving here on Earth.
Exactly right. The opportunities for technology transfer from this mission to go to the moon and Mars and grow plants for human life support. You go to the moon and Mars, you can't throw anything away. There's no such thing as waste. You must recycle all the water, all the carbon, all the nitrates, all of the ions, as you mentioned. So we don't know how to do that yet. Sensor technology is part of the issue, but we cannot, as you say, maintain a sustainable kind of bioregenerative, self-sustaining life support system in that way. And learning how to do it in space will definitely improve our chances of managing ecological contexts here on Earth. We did some work some years ago with one of my grad students, Jeff Waters, and worked with Gene Hunter from Cornell, a nutrition specialist, and we developed a menu, a nutritious, well-balanced vegetarian menu with a 10-day menu cycle and a crew of 6 or 8, as I recall, and determined, okay, so you have to have these many commodities on your plate, and it takes this much space to grow that. And we determined at the time, and this is about 15 years ago, that it takes about 73 square meters of plant production, and a lot of it was wheat and soybeans and staples, rice, wheat, and soybeans, that sort of thing. But 73 square meters per person for all of the life support requirements, and that was driven entirely by food. If you grow enough food for one person, then you have double the CO2 scrubbing, the oxygen generation, and the fresh water recycling capabilities of the plant system than that crew member needs. So food drives it. We've since learned that, driven that number down, and that's been the mission in biological life support research agendas around the world. The mission is to drive that 73 square meters per person down, because that represents the mass and energy cost of life support. And I think we're down around 50 or 60 now, based on improvements in energy with LED lighting, high efficiency LED lighting, and mass. We got the pressure down. We did a lot of work in the early years on pressure in our facility. If you can reduce the atmospheric pressure of the life support system, then you necessarily reduce its mass, the structural mass of the system. So you can consider low mass inflatable structures that don't require full Earth atmosphere. So we've made a lot of progress, and I think we're down around 50 or 60 square meters per person, but that's still a lot.
So this research that you're doing, I know about 10 years ago, we collaborated on an NSERC collaborative research and development project called Entice, which was innovative technologies in challenging environments. And I recall we built some serious research hardware together. Can you tell our listeners about this hardware and what you've been using it for?
Well, we were mostly starting to look then at LED lighting. We worked with a company from Norway, which has since moved a significant portion of its operations to Canada, Intravision Light Systems, and we developed a lamp that could generate over 5 times the intensity of the sun inside one of our chambers. And I remember testing that. We had to wear welder's goggles to test it, and we have since improved that lamp. It's a water-cooled lamp, of course, to have that much energy in a small space. And we have improved it to the point where it's now something like 7 or 8 times the intensity of the sun. But the new improvement, we have never turned it on full blast because we lost our welder's goggles in the lab. Nobody had the guts to turn the damn thing on full blast.
So you're using that to look at how plants interact with light and improving the recipe of different wavelengths?
That was the origin of our sort of space exploration agenda at Guelph. And we've gone on then to develop all kinds of technologies out of that basic fundamental requirement to jam stuff in a small space and make it work.
You've almost single-handedly built this field of research in Canada. Many of your graduates have gone on to great success. Can you describe some of the work that's come out of your group?
I guess I should have made a list before we started here. I get a lot of really good people working in this, and I've had people stay with me, for over 20 years in terms of the technical staff. Jamie Lawson and Teresa and Mike Stasiak are sort of the core of what we do here and maintaining. But Tom Graham came as a PhD student and a postdoc, and then went off to NASA and spent 3 years there as a research fellow. He's now back as a full-time faculty. He's got the most recent faculty position in the controlled environment area. Matt Bamsey, of course, who did a PhD in my program and then went to Florida, worked with Rob Furl and Annalisa Paul, and then went off to Germany, had a Marie Curie fellowship with the German Space Agency and worked with Daniel Schubert and did a lot of actually he worked on a project we had, he and Tom Graham were up in the Arctic at the Devon Island Mars analog greenhouse, the Arthur C. Clarke Mars greenhouse on Devon Island. And then while he was in Germany, he was a great deal of the ground management of the Eden ISS project, where we put a food production system in the Antarctic in collaboration with the German Space Agency and a long list of a dozen other institutions and industry partners. So, and that's still happened. That's still operational, although the funding ran out for our end. But they're still growing tomatoes down there in the Antarctic for the German Space Agency.
That's pretty cool stuff. You've also had some commercial spin-offs that have been successful. I think there's a Living Wall group.
Right. That was actually the very first science project, I guess, we did in the context of atmosphere management. We were mostly concerned about ethylene, but carbon dioxide and oxygen, the general life support gases of interest, but ethylene can accumulate when you have a lot of plant material.
Now, before you move on, ethylene is a compound that causes plants to age
and die. It can, if it gets to pretty high levels, it can wipe them out. It's a sort of a growth regulator kind of compound. It's a trace hydrocarbon in it. And but it's a very powerful growth regulator. You only need a little teeny squirt of it in the atmosphere, and it messes up how plants. I mean, that's why that's what your mother does when she puts the tomatoes in a bag on the windowsill. The ripening fruit naturally gives off ethylene, and if you put it in a bag, then the ethylene accumulates and accelerates the ripening so that you get to eat the tomato. Or if you import bananas from South America in the wintertime, they come here and they're just as hard as a nut. But you hang them up in a locker here in the Loblaws food terminal over here in Cambridge and close the door and gas them with ethylene. And that makes the bananas ripen so that they turn from green to yellow. So those are the applications of ethylene. But in a life support system, if it accumulates beyond some very, very trace levels, it can have disastrous effects. On the space station Mir back in the mid-90s, when the Russians and the Americans had some experiments with wheat, Frank Salisbury collaborated with the Russians and did some wheat experiments on Mir, and the wheat grew, looked great, came back to Earth, opened up the seed pods, no seeds. And that was because of ethylene. The average ethylene concentration over that period, when they look back at the GC history, gas chromatography history, was about 1.2 parts per million, which doesn't sound like a whole lot, but that's 1,200 parts per billion. And plants start reacting to ethylene concentrations around about 50 to 80, certainly less than 100 parts per billion. So when you're at 1,200, surprise, surprise, you have a disaster with your reproductive systems.
Wow, that's cool stuff. So, I mean, you've done some really cool things. What are what's the coolest thing you've done? Is it the Houghton Crater stuff?
Well, that had its moments. I was never allowed to go there because it cost too darn much to send me up there as a tourist. You had to be up there with a hammer and a screwdriver, or you weren't allowed. But you mentioned, and I forgot, you mentioned the biological air filtration. We're looking at atmosphere management in closed spaces, and what spun out of that was what's called biological air filtration. So that was eventually commercialized under the auspices of the Ontario Centres of Excellence. They provided a grant to one of my grad students, actually a postdoc at the time, Al Darlington, and he set up a company then that commercialized this technology in domestic applications. So office buildings, especially the Canada Life building was our test venue back in the day. So this is back in the early 90s. And since then, the company that Al founded was eventually bought by a bigger company, which is, the way it goes. And it's now called Nedlaw Living Walls, and it's part of the Walden Roofing family of companies. Nedlaw is Walden spelled backwards, so Nedlaw Living Walls here in Breslau, Ontario, just down the road, still operates. In fact, we have just set up a collaboration with that company. They're having, a few technical issues with some of their larger biofilters in the local area, and they want us to help them come up with management strategies, especially the horticulture and water management strategies based on some of the technology that we can put in the field on their behalf and the expertise from my team. So we've just started up a new collaboration with that company and have collaborated with them over the years on a number of research projects. But that was one of the more successful commercialization opportunities that grew out of our program.
So these are basically walls full of different plants that filter the air, and they're decorative.
Right. It's since it's indoors, it's relatively low light. So you would choose understory, tropical plants kind of thing, in conventional house plants. At one time, we thought the kind of plant mattered in terms of its contribution to atmosphere management. It doesn't. And the other thing is, and this is tough for most, because the media doesn't help us much. Plants don't clean the air. They have the metabolic chemistry for photosynthesis, so they can suck up CO2 and spit out oxygen and fresh water. But they have a hard time with xylene and methyl ethyl ketone and all the toxic chemistry that we associate with poor quality indoor air is not food for the metabolic process of a green plant. However, green plants leak photosynthetic products out of their roots, so carbohydrates, sugars. They have root exudates of a whole range of chemistry that services and supports the microbial community in the root zone. And so we've created the root zone on a porous medium so that there's a lot of biofilm associated with the root zone, and the microbial community survives in this biofilm, and the biofilter is a wall built on a porous medium, and we're giving all the technical specifications away here, but that's okay. So that this porous medium that's full of roots that are leaking sustenance into the microbial community that lives in the biofilm, and then you start sucking in with high volume, low, or I guess just large volume air movement, but not very fast, big, slow, lazy air movement through the substrate. The chemistry that we associate with poor quality indoor air, like xylene and the stuff that comes off of paint, toluene, etc., they're highly soluble formaldehyde, highly soluble compounds, and once they dissolve in the biofilm, then the microbes that do have metabolic processes to consume those, metabolize those compounds into CO2 and water, and the process that's kind of the way the planet works. This isn't rocket science, I must say. But the misconception that the media has given to, and still persist in doing so, that green plants clean the air. There are even webcasts or podcasts you can see from these snake oil salesmen, I'll call them, who claim that you have a dozen potted plants in your living room and you're going to live forever. It cleans the air. Well, it doesn't work that way. The root zone and the microbes that live there off the root exudates. So the green plants are absolutely necessary, They provide the sustenance that sustains the diverse microbial ecosystem that is actually the machine in air filtration. And we just create a technical context and configuration of the root zone with a large surface area and a lot of biofilm. That is the machine that cleans the air.
Yeah, that was a shock to me when I found out about that as well. Is wow, it's the microbes. That's the keys, is the microbes, and that's the soil. That's what soil is a microbial ecosystem, right?
Exactly, and microbes win. I mean, they're going to get us eventually.
So, as with any prophet of change, you've been, I think, more successful internationally than at home. Can you describe some of your international projects and how your group has kind of been leading the world in abroad?
Well, we're as a relatively unique, I hope it doesn't stay that way, but as a unique life support research venue in Canada, there are slowly but surely being groups that are starting to take on, like McGill, Mark Lefsford's group, etc. There are others who are starting to pick away at some of the technical challenges here. I think the work we've had with the Melissa project, Melissa is the European Space Agency's life support program. We joined it as a partner in 1997. And have been collaborating and participating, and I guess contributing the higher plant, the food production side of the life support system that Melissa represents. Melissa is largely a recycling system, based on recycling all the carbon, oxygen, water, nitrogen, etc. And we come along with the higher plant expertise and contributed the so-called higher plant compartment of the Melissa loop. So we built a system for them and installed it in Barcelona.
Nice place to visit.
It is. The university in Barcelona, the Autonomous University of Barcelona, is the home of the Melissa pilot plant, and we have a chamber installed there, and we provided personnel for a few years to operate it and do the tech transfer, if you will, from the Canadian life support program, the SALSA program, to the Melissa project. And we've also worked quite a bit with NASA, of course, our good friends at Kennedy Space Center, where Tom did a postdoc and a research fellowship there for a few years. Ray Wheeler, who's the head of that life sciences group at Kennedy, is a close friend, and actually with me is the author of getting barley on the list of candidate crops for human space exploration.
That's a very important piece.
It took me almost 20 years to get that resolved, but that story.
Yeah, and the Barcelona angle is also very nice, because I remember we were at a conference on life support in Barcelona the year Spain won the World Cup, and we were there for the finals, and they had this huge set up in the main square in Barcelona, like 1 million people watching big screens.
I remember.
That was a fun time. So, how's the future looking for advanced life support? What's on your agenda?
Well, the Canadian Space Agency has had a lot of sort of interactions with the general scientific community in Canada for the last year or so. The Phase Zero project on putting plants on the moon on a lander that we're working on right now, that has plans to go Phase 0, 1, 2, 3, etc. We will land plants on the moon in the next probably 2 or 3 years. We will participate with a lander. There's going to be so many landers that the options are many and varied, and so surely one of them will have a little space for our little crop of barley on the surface of the moon. So I'm looking forward to that happening very quickly. There's also a recent call for topical team. So this is very reminiscent of what you and I participated in as the discipline working group. They're now calling it topical teams, and the food production topical team is one that is currently calling for proposals. So we're putting that together, and hopefully we'll have some contribution there. Even if we don't win that proposal, whoever does will hopefully start looking for some additional contributions to their discussions from guys like us.
Yeah, I really like the idea of developing technologies and science for space applications that have obvious and direct secondary applications here on Earth. And if we can build it here on Earth, then we can build it on the moon and vice versa.
Right. Food production is probably the richest source of the technologies and research required to grow plants for life support on Mars or the moon, for example, is easily, in my mind at least, maybe I'm biased, but the richest source of technology transfer to terrestrial applications that I can possibly imagine. It is, potentially an economic engine for a country like Canada that'll service us for the next 300 to 500 years if we last that long.
Well, I hope to. So we're coming to the end of our time slot, and I have one final question for you. What's your rarest scotch?
Well, I have a 30-year-old Dewar's, and it's a blend, which is almost sacrilege. But I was in a duty-free store somewhere in Europe, or I can't remember, maybe it was in China or Hong Kong, and I got to taste this. Otherwise, I would never have bought it. I mean, it's a blend after all. but it's a 30-year-old blend, and it is quite remarkable. I guess it's my rarest. It's probably my most expensive too. But the best, I guess, would be, and you got to get into the 20-plus-year-old ones. I had a 25-year-old Nochendu, which is a Speyside. It's a very tiny little distillery, but an extremely unique bottle. And I had this 25-year-old that I picked up in Paris at there's a store there that sells only single malt whiskey. Glorious place. And I went back there last year, I guess. No, last year didn't exist on my calendar. The year before, I went back there and to try and repatriate that bottle to my shelf, and they didn't have any, and they don't make it anymore. They only did it once. Nochendu only did a 25-year-old once. So I had to relegate myself to the 21 and the 18. Both are stellar. I highly recommend them, unless you go into stores that are in my area and you only see one of them. If you buy it, I'll kick you.
Well, very good. Well, thank you for joining us on The Rational View and sharing your research with us. It's been a great pleasure to revisit old times and see what's going on in ALS. Thanks very much.
Okay, Al.
If you're enjoying what you're hearing, please consider visiting my Patreon page and becoming a patron of this podcast at patron.podbean.com/TheRationalView.